Hello, physics students. This is Dr. Brenzi. This is lesson 6.1.1, and today we're going to be able to describe and calculate the magnitude of a mysterious force that attracts all of us to one another. Well, it's pretty appropriate we should talk about a force like that pretty close to Valentine's Day, because, you know, we like to be attracted to other people, and there's something romantic about physics telling us that there's some sort of attractive thing that attracts all of us to one another. But what is this mysterious force? What I want you to do is I want you to open up the PDF file that you also have on Edmodo along with this video. If you haven't done that yet, I would encourage you to go back to Edmodo and download the lesson 6.1.1 PDF file and open it. And you'll need to navigate past the do now problems to a table that shows Toto, Peyton Manning, and Serena Williams. So what this table shows, it shows this mysterious force that attracts Toto to Peyton Manning, it attracts Peyton Manning to Serena Williams, and it attracts Toto to Serena Williams, and it also works in the reverse direction. So if Toto is attracting Serena Williams in turn is attracting Toto. So there's a table there. Actually, for some of you it might be two tables for the advanced class. But I want you to figure out how this mysterious force depends on the mass of the two bodies that are attracting one another, and how it depends on the distance between the two objects. So go ahead and pause the video. Take a look at those tables and see what you can observe by looking at those tables in regards to our mysterious force. Okay, welcome back. Well, hopefully you came up with the following observations just by looking at this table. So let's go ahead and do that. First of all, you probably notice that this thing is a really, really weak force. Okay. You notice that there were we're talking like 10 to the negative 11 newtons and stuff like that. So it's really, really weak. Not a very strong force at all. Hopefully you observe that it also increases with mass, so the combined mass of the two objects. So the more mass of these two objects are, the more gravitational attraction is between the two. Oops, I gave it away, didn't I? Uh-oh. Well, so did my word up here. But anyway. And you should have also figured out that this force decreases with the distance between the two objects. So the farther they are away, the less gravitational force is attracting the two of them. And yeah, I gave it away. Oops, my fault. It is gravity. This is our mysterious force. And yes, gravity attracts everyday objects like you and me toward one another. We don't think of it that way because it's such a weak force, but it does happen. It is a force that attracts any two objects that have mass. Now, Newton was the person who first proposed this. You might think back to the famous apple falling on his head, and that's kind of what prompted Newton to start thinking about why masses are attracted to one another. And this was the result. So what Newton discovered, he actually came up with a formula, and you might have been able to figure out the same, is that this force is equal to a constant, g, times the combined masses. So you have two masses, m1 and m2, you multiply those, and then you divide by the distance between the two of them squared. Now this constant g is equal to 6.67 times 10 to the negative 11 when we're dealing with MKS units. And that is a universal constant. So throughout the entire universe, we physicists believe that this holds for any two objects in the universe that have mass, that this gravitational force is working between the two of them. What you'll see next is a set of group practice problems, and if you making this class up, what I want you to do is I want you to try those group practice problems. Under the group practice problems, you're going to see a table of astronomical data because gravity is a very small force unless you have things that are very, very massive, like planets and stars and stuff like that. So those are the types of things that we're going to have to deal with in this unit. So you have a table of data there, and for each of the planets, or in case of Pluto, which recently got demoted to a dwarf planet, you will have some information about it. You'll have the mass of the planet, you'll have the radius of the planet, and you'll have something called the orbital radius of the planet. So the radius of the planet is just the distance from the planet's center out to its surface. That's pretty simple, right? Some people got confused about what orbital radius is in class. Well, that is the distance from the planet's orbit to the sun. Okay. So when you're looking in that, I think it's the fourth column, and you see orbital radius, that's the distance that it's referring to. Okay. So when we're talking about attraction between a planet and the sun, we probably want to refer to orbital radius. Whereas if we're talking about somebody on the surface of Saturn, or if they're floating around in orbit around Saturn, we probably want to deal more with the radius of the planet. So go ahead and attempt those group practice problems, and when you're finished, resume the video, or maybe you can just resume the video and then try the group practice problems later. Either way should work for me. Okay, whoops. I'm getting ahead of myself. So, one other thing I want to talk to you about in this lesson is why does little g change on different planets? In other words, another way of putting that is why do you weigh different weights on different planets? Like, for example, why do you weigh less on the moon than you do on Earth? Well, here's an equation we know and love. We know that the force due to gravity when we're on the surface of the Earth is equal to m times g, and this little g changes from one planet to the next. Like on the moon, it's like 1.6, and on other planets, it can be greater or smaller. Why in the world, however, does g change, little g? Well, we just learned that universal gravitation says that the force due to gravity is equal to big G times big M times little m. And we're going to assume that big M is the mass of the planet, and little m is our mass, the person sitting on the planet. And then we take G, big M, little m, and divide that by the radius of the planet squared. So this is the force due to gravity if we're sitting at a radius r away from the planet's center. Well, these two things are both describing gravitational force, right? So what we should be able to do, they should be the same thing. So if we set these two equal to one another, we get this equation right here. And if we do a little simplifying, we notice that the m's could divide out if we divided both sides by m. And we're going to end up with little g equals big G, big M divided by r squared. Well, what does that tell us about little g? It tells us that little g depends on the mass of the planet, and it depends on the planet's radius. So if you're on a more massive planet, you're going to experience a higher acceleration due to gravity if the radius were the same. Or if, like say, the radius of the planet is smaller, but if the mass remained the same, well, a smaller radius means that this number is smaller, and when you divide by a smaller number, you get a bigger quotient, so that having a smaller planet would result in a larger value of g if the mass were the same. Okay. So that's a reason why your weight changes on different planets. It changes on the moon because the moon is less massive, and it also has a smaller radius, and between the two of those, it turns out that little g on the moon is about 1/6 of little g on the Earth. Well, would G change if you were in orbit around the Earth? If so, then how? So I want you to think about this, and then when you're done, go ahead and resume the video. Okay, we're back. So we know that the acceleration due to gravity on the Earth itself, and by the way, this is a little shorthand symbol you can use for Earth. It's a circle with crosshairs, I suppose. That's a shorthand symbol for Earth, so I put that right here. And you can start using that too. It's going to save you a lot of writing. So the acceleration due to gravity on the surface of the Earth is equal to G times m over r squared. And if you were to actually plug in the mass of the Earth and the radius of the Earth from your table and plug in the value of G, you actually are going to get a number that's pretty close to 9.8 meters per second squared. Well, what is going to happen if we decide to go up into space a distance of twice the radius of the Earth? I'll let you think about that for a little bit. Look at this equation and tell me what might happen if we decide to go a distance of twice the radius of the Earth. What will happen to our acceleration due to gravity? Okay, welcome back. So hopefully what you recognized is that the acceleration due to gravity out here in space at a distance of 2 times r is going to equal to G times m times a quantity 2r, all of that squared. And if we do a little simplifying here, that turns out to be Gm over 2 squared times r squared. And if we pull this 2 squared out in front, we're going to get 1 over 4 times G times m divided by r squared. So the acceleration due to gravity out in space at a distance of 2r is equal to 1/4 the acceleration due to gravity we'd have on the surface of the Earth. So if you double your distance from the planet, you are decreasing your acceleration due to gravity by a factor of 4. Okay, so those are all the things I want to talk about to you in this lesson. Go ahead and try the group practice problems, and if you have any trouble with them, come talk to me during class. And the independent practice problems are at the very end of the packet, and those will be what you will need to turn in for a grade. All right, hope this helps, and I'll talk to you soon. Bye.